over the course of the next several weeks, Sabin Russell will engage lab staff about the ins and outs and ups and downs of innovative science. But of course, as always, we also want to hear from you, so there'll be plenty of time for questions at the end of each talk. Please wait for a microphone before you begin your question. One of the first questions that might be on your mind, which I'll answer now before handing the stage over to Sabin, is who is Sabin Russell? Sabin joined Berkeley Lab last year after a long career as a Bay Area health and science reporter, including 22 years at the San Francisco Chronicle, freelance work for the New York Times, as well as a Knight Science Journalism Fellowship at MIT. He's best known for his coverage of HIV in the US and Africa, but he's also covered a wide range of topics, including the Columbia shuttle disaster, as well as the tsunami in Sri Lanka. He is now the lead editor and writer for the Creative Services Office, which is a public affairs unit that writes, edits, and produces documents for the entire lab. So I will now hand the stage over to Sabin, and for our first installment of Sit Down with Sabin. Thank you.
Thank you, Dan, and thank you all for coming today. This is a bit of an experiment. We hope you'll find it entertaining as well as interesting. As somebody who was new to the lab, one of the things that struck me almost immediately and still strikes me today is the diversity of science that's pursued in this institution. You can go to the molecular foundry at one end where they're talking in nanometers, and you can go down the hall where they talk in megaparsecs. And at the ALS, they have X-ray beams as thin as a hair that are 1 billion times as bright as the sun. And then you go over to Building 90, and there are people there who are figuring out how to paint roofs white and put coatings on windows and maybe save the world in that fashion. And that just scratches the surface of how interesting and diverse a place this is. So one of the other purposes of this is that we have a broad diversity of people working at the lab. We also have student interns working here. We have high school students in the audience. We have college interns, we have postdocs, and we have staff scientists. So the purpose of this particular conversational style is to maybe dial down the science a little bit and present it in a way without PowerPoints, relying on our own words and a conversational style to make some of the work that various people are doing here more accessible to all of us, and perhaps in a little more relaxing fashion than the kind of academic lecture format that we do as a regular part of our jobs here. So since we're dialing down the science, I couldn't think of anything that's more of a no-brainer in kindergarten science than dark energy and the ultimate origin and ultimate fate of the universe. So with that introduction, we have one of the best people I know to talk about that subject in a conversational style, David Schlegel. He's a senior scientist with the physics department at Berkeley Lab. He is the principal investigator for a project called BOSS and a forthcoming project called Big Boss that we'll be talking about quite a bit in this session. The session is called The Hunt for Dark Energy, and here we have a hunter for dark energy. He got his BA from Princeton, his PhD from Cal. He's been working at the lab. He's a senior scientist. He's been working at the lab since 2004. So I'm very pleased to introduce David Schlegel. So our topic, David, is the hunt for dark energy. We'll be using the term dark energy a lot throughout this conversation and getting into more and more detail over time. But I think that just because there is a diverse group of people here, let's just start right out with the basic question of what is dark energy, why is it dark, and why are you hunting for it?
Okay. Some good kindergarten questions there. Well, let me just step back for a moment here and just put a little bit of historical context here, which is just to start by saying that right now in cosmology, so the study of the cosmos, we really are at a time of maximum ignorance. So I think it's the case that there's no time previously in history where we knew there was so little that we knew. No. So, I mean, you can go back to previous times where maybe our worldview was incomplete or wrong. There was this view going back millennia that there was this crystalline sphere that the Earth was in the middle of, with the stars and the planets implanted on other crystalline spheres orbiting the Earth. And okay, maybe that wasn't right, but it was kind of a complete view of what the cosmos looked like. Okay, so then jumping forward a few thousand years, we did have the Big Bang figured out at some time in the middle of the 20th century as the formation of the universe from the Big Bang. But then more recently, in recent decades, what we've discovered are just the big pieces of the energy density of the universe that we're missing. Okay, so one of the big pieces that's missing is dark matter, which we're not going to talk about very much today, but it's worth mentioning because it actually outnumbers normal matter in the universe. So you look around you, everything that we're sitting on, these are made out of protons, neutrons, so baryonic particles, which we know now is only about 4% of the energy density of the universe. And there's a dark matter, which are particles that exert gravity like normal matter, but is 6 times more abundant than protons and neutrons. Okay, so that was one of the first pieces here. I'll get somewhere.
And you're talking about this famous pie chart that we now have of the energy density of the universe. 25%, roughly 25% is considered to be dark matter. Roughly 5% the baryonic matter that makes up what we see here and what we see when we look up in the sky. And then close to 72% of the universe is dark energy. And why, if there's something that big out there, do we need to look for it?
Because it's there. So this was the new piece that no one was expecting. I mean, I think it's fair to say no one was expecting dark matter in the first place. I mean, that's weird. And then dark energy, this is something that was only discovered in 1998.
Right here.
Right here at Berkeley Labs. This is a group led by Saul Perlmutter, and there was another competing group at the same time. So it was discovered completely observationally, and it was discovered by trying to map out something that we already knew, but we didn't actually know at all. Okay, and this was looking at the expansion history of the universe. So it was supposed to be a straightforward experiment that would kind of return the answer that we knew, that we didn't know.
It was to see whether how fast the universe is slowing down, basically. Was that more or less the goal of the experiment? And instead, the experiment found in 1998 that the universe is not only expanding, but that expansion is accelerating, which in the world of physics is a little bit equivalent to tossing this bottle up in the air and seeing it continue to rise and accelerate even faster. It seems to violate the laws of physics that at least that I know. And I understand that the term dark energy is basically a placeholder term for what we don't know. Dark energy isn't necessarily energy. It isn't necessarily, we have no concept. We do have a concept of what it is, and that's really what we're going to be talking about further. There are several theories, but any one of those theories makes a mincemeat of some of the fundamental laws of physics as we've known them. Or am I overstating the case?
No, I think that's fair. I mean, so the term dark energy, it was coined to really describe this observation that we don't understand. And so the observation of the universe so it was decelerating for about 7 billion years. So you had the Big Bang. Everything seemed to obey the laws of physics for the first half of the age of the universe, in that everything attracts everything else. So there's through gravitation. And so that slows down this expansion. And it was slowing down for about 7 billion years. And then about 7 billion years ago, everything started flying apart even faster. And then you can ask yourself, what could account for that? And one way to account for that is to say that there's an energy term innate everywhere in the universe, where once the universe becomes diffuse enough from its own expansion, then this energy term becomes dominant, and actually it dominates the expansion.
So we're talking about a force that, unlike the attraction of gravity, is kind of a repulsive force that seems to be causing the universe to run away from itself. Not so long ago, an author, Richard Panik, was standing right at this very spot talking about his new book, The 4% Universe. And in it, he talked about how there was a moment in 1610 when Galileo first invented the telescope and started to discover that there were things about the world that were accepted, that there were things we did not know about in the world, and with this instrument, new things were revealed, and it certainly changed the way the world was viewed. And
that instrument being the telescope.
That instrument being the telescope. And Panik is making the point that he feels that at this moment we may be, in a sense, reliving 1610. He feels that these discoveries of an accelerating universe, of dark matter, are so significant that this pie chart that shows 72% of the universe is composed of dark energy are so significant that we are reliving 1610. Now, would you agree with that in terms of a paradigm shift?
I think so. I think some of us think that. So there's, I mean, I should say there are differing opinions on this. So there's also, within just the field of kind of astronomy and physics, I think there are some people who think, well, you could actually explain this phenomena of dark energy with a simple cosmological constant, which is, so it's one possible explanation for dark energy that's kind of the simplest modifications you could make.
This is the cosmological constant first posed by Einstein,
right,
and then later rejected by him as his biggest mistake, supposedly.
Yeah, so this was something, so just to go into the history here, this was when Einstein figured out general relativity, which is also an interesting story. What he found was the universe wanted to be dynamic. It wanted to expand or contract. I mean, you have all this gravity acting on everything. But we knew that the universe was static at the time, that it'd be crazy to have a Big Bang. So he had to do something to fix that. Mm-hmm. And so to fix that, he put in this term that would exactly balance the expansion-contraction of the universe or the contraction that you'd want from gravity. You know, if Einstein hadn't done that, maybe he'd be famous today.
Well, so the National Research Council laid out 11 scientific questions for the 21st century and said that determining the nature of dark energy was the most vexing of those 11 physics challenges for the 21st century. And this is essentially what you do. You are a dark energy hunter. So you know, some hunters have bows and arrows. What is your weapon? What is your instrument for discovering dark energy?
So all we have is the universe to look at. What we're doing is trying to chip away at either pieces that don't fit or where we think we might be able to find a clue. And unfortunately for dark energy, there aren't a lot of clues yet. Okay, so but there might be more than one, which is also another debatable point. But the the evidence that we have right now is this accelerating expansion that was discovered in 1998. So we've seen this now from lots more observations in the past decade, and we've confirmed this many times over that, in fact, the universe is doing this today. So that's a measurable that we can go after, this expansion history of the universe. So as a function of time, how big was the universe? So that's the first piece that we can go after. I think the hope is that this whole notion of dark energy, or whatever it is, or whatever we're calling it 10 years from now, after we figure it out, or 20 years, or 50 years, is that, or 1 year, I don't know, let's be optimistic, is that this might fit in with some other pieces that are also as yet to be understood.
So as I understand it, what you are basically doing is trying to create a three-dimensional map of the universe and use that map as a tool to understand the behavior of dark energy over the course of, 13 billion years. And so essentially, your method of zeroing in on the behavioral characteristics of dark energy is to build this three-dimensional map. And in order to do that, this gets us into the telescope and the instruments that you're involved in, the BOSS and the Big BOSS projects. And so to describe what I think is extremely interesting, the actual instruments that you're using and why you're using them, why don't you show us what you brought?
Okay. So let me just start with what you're saying is the measurements we make, they're geometrical measurements of what the universe looks like. So that's the tool that we have. And then getting a little more physical here, this is, this could be many things, but what this is, well, one thing this could be when
we'll be serving pizza
there we go.
After the event.
So the thing I think of when I look at this, by the way, is this is also a pretty good model of what the Milky Way galaxy looks like. So to digress for a minute here, we are lucky where we live in the universe in that we do live in this Milky Way galaxy. It's this thin array of stars and dust. And we don't live in the center, which is very lucky. There are lots of stars in the center. There are probably lots of planets in the center. But if you lived in the center of the Milky Way, you wouldn't actually see outside the Milky Way at all. And we wouldn't be having this discussion for maybe 1 million years. I don't know. You'd have to actually get out of the Milky Way to actually observe anything. So anyway, sorry, it's just thought-provoking when I look at these plates.
This is a man who knows a lot about galaxies.
So what this plate is, so we're making a map of the universe where what we're making is a three-dimensional map of the universe where, and it's a hard thing to do. When you look up at the sky, you see the planets, you see the stars, you see other galaxies, and actually when you just look, even if you look with the telescope, it's not obvious what's nearby and what's far away.
So you could have a very bright galaxy, but you don't know whether that's a giant galaxy that's very far away or a small galaxy that happens to be close. And essentially we deal right now with two-dimensional pictures of the universe, like the Hubble Deep Field pictures that many of you have seen, where we see that the universe is just absolutely chock full of galaxies. I think that was kind of a new idea in the last 30 years or so, that not only do we have some neighboring galaxies, but there are, 100 billion galaxies? There are many galaxies in the universe as there are stars in the Milky Way. And that this device right here is a way of measuring, of zeroing in, of scanning the sky, a piece of the sky, right? Mm-hmm. And measuring through each of these dots the redshift, which is a kind of a Doppler-like effect, to determine how far away those galaxies are. And so to those, is this visible to people way in the back of the room? Can you see that this thing is full of holes? And each one of those holes is what?
So these are, what we do is, so this is something that goes in the back of the Sloan Digital Sky Survey telescope.
That's in New Mexico?
In New Mexico. And every observation we make, every hour, we have one of these plates manufactured. We have thousands of these now. They're heavy. Very precision machined aluminum, extremely flat, apparently. And everywhere we're going to point on the sky, we already have a two-dimensional map of where all the galaxies are. And so we say, okay, we're going to be pointing here for the next hour. We need a plate where we drill a hole at the location of each galaxy that we want to observe. So this plate goes on the back of the telescope. And then there's a guy who actually takes, how about my other prop here? These are fiber optics, just like you find, well, anywhere now. And there's someone who actually, before we start observing for the night, takes all these and plugs them into all these holes on the back of the plate.
So you have to plug every one of these holes with a fiber optic cable to read an individual redshift for an individual galaxy.
Yeah, so it's an interesting mix of technology from switchboards in 1900 and then some 21st century technology, right? So rather than wire, right, these are fiber optics, and then these lead down to an instrument that has CCDs on the back of it.
So you've got the lens of the telescope out here somewhere. It's projecting the image of a piece of the sky. About how much of the sky does this thing scan at one moment?
So this telescope was designed to survey as much of the sky as possible, and that's what's unique about this telescope. So it can see a field of view. It's 3 degrees across, which is...
How's that compare to, say, the width of the moon, a full moon?
So the moon is half a degree across. So it's much bigger than the full moon.
So this is a fairly large chunk of sky.
And then if you compare it to Hubble, the Hubble telescope, it's a great telescope being in space and above the Earth's atmosphere, but it has a much smaller field of view. That's the equivalent of taking a soda straw that's 8 feet long and looking through it. So you could use the Hubble to survey the whole sky, but it would take something like 400,000 years.
So this thing has been precision machined. Every hole represents a galaxy. I can hold this very still, and I can see the earring in the ear of the woman up there. So this is pretty amazing tool.
It's not supposed to magnify it. I don't know.
And so how many this is the BOSS project, correct?
Yeah, so the BOSS project, this telescope actually began operations in 1998. So coincidentally, it might even be to the month that dark energy was discovered. That's when this telescope turned on. And then we didn't know about dark energy at the time, so it wasn't designed to do that at all. So what the Sloan project started to do was it first did this program for 8 years of mapping. It was the brightest 1 million galaxies on the sky. And so it completed that project in about 2008. But we've retooled this telescope and instrument now to actually look at a much, much larger volume of the universe. And so now we're looking at another 1.5 million galaxies that span about halfway across the universe.
So we're talking about a survey that will map the distances of a total of, I guess, 3.5 million galaxies when it's done?
2.5.
2.5 million. I'm an English major, so please forgive me. But okay, 2.5 million galaxies. We'll know how far away they are, and stretching back 8 billion years, and then when this project is completed, there is the project called Big Boss, which is, I would presume, a bigger version of BOSS. Tell us a little bit about that project and in its goals.
Right. So these projects, of course, take many years to build at the same time. The BOSS project on Sloan right now. So we are making this. It looks like a very ambitious map of 2.5 million galaxies, then out 6 billion light years. The problem is it still doesn't actually get out to that time in the universe when we think the universe went from being decelerating to accelerating. So that's inferred from...
So some sort of very important transition period in the history of the universe, and this one really can't do the job.
Right, it might be. Again, we don't really know.
Mm-hmm. So Big Boss, as I understand it, its 5-year goal is 20 million galaxies?
That's right. So about an order of magnitude more than what we'll have completed with Sloan several years from now.
And I understand that the device for Big Boss, it would be outfitted on the Mayall telescope, which is at Kitt Peak in Arizona, and it will be surveying how many holes are in this one?
So this has 1,000 holes.
This has 1,000 holes. We're going to a 5,000 hole instrument that will be capable of surveying how many galaxies and celestial objects in a single day, a single night, I should.
Yeah, usually at night.
Yeah, at night. Good point.
So it would be about 200,000 in a clear night.
200,000 celestial objects will be measured. We'll know how far away they are. So somewhere there's got to be a very large computer gobbling up this information that you're going to be generating.
It's downstairs here right now.
It's downstairs. Everything seems to be at Berkeley Lab. And what about the poor guy who has to put in 5,000 of these things?
Yep, so his name is Norm Blythe. He's retired. We've replaced him with it's 5 other people doing the plugging operation today. So we don't think that manually, plugging holes 200,000 in a night is actually the answer when we start this next project. So the replacement, so finally, we think we'll be replacing this plug plate kind of design with a robotic system. So what we're designing right now, it's a focal plane, so focal plane meaning where everything comes into focus on the back of a telescope. So on this focal plane, rather than a plug plate, will be a machine actually with 5,000 little robots, each with 2 motors, driving around fiber optics.
So these fiber optic cables, these 5,000 fiber optic cables will all be in place, and we'll use computers and actuators of some kind to actually point the fiber optic cable to the target, and you'll be scanning a piece of the sky every 15 minutes.
Right, that's the plan.
That's amazing. So this amazing instrument, how much is this thing going to cost?
Oh, are we being recorded here? So the construction budget for this is about 70 million. And then you have to operate the telescope, which, there's an expense to operating any of these telescopes. But the other way to look at this, or the way I choose to look at this, is you can try to do projects like this with space missions as well, which have some advantages.
They also can blow up.
They could blow up. They're also expensive. So
A lot more expensive.
Yeah.
So this is the cheap method of getting a 3-dimensional map of the universe. And
and it turns out you don't need anything too exotic to actually make these maps. You really just need this sort of technology multiplexed. So this is really taking advantage of fiber optics, CCDs, all of the things that we kind of take for granted today.
So these are the tools. The goal is a 3-dimensional map of the universe. And with that 3-dimensional map of the universe, we're going to find something about the way dark energy exerted its influence on the expansion of the universe over a period of perhaps 8 billion years. So in a sense, it's dark energy from maps. I know that we've talked about dark energy as one of the most vexing problems. There are multiple theories about what dark energy could be. Can you describe a couple of examples, theory A and theory B, and how and what you would expect to find using with your three-dimensional map that might lead you to either rule in or rule out those options?
Not very well, but I can try. There are more expert theorists on this than me for sure. So one of the ideas here is that you could add this, we talked about this earlier, this cosmological constant to Einstein's theories of relativity to kind of balance those equations and put in this extra term that could explain the expansion history that we're seeing.
Is it sort of a mathematical explanation?
It sort of is, and so even if it is this cosmological constant, the theorist would still be asking the question, well, what can actually cause this sort of effect? And then, I don't know, there are all sorts of, I don't want to say crazy ideas, different ideas. So some of them having to do with interactions with the four-dimensional space that we live in, where this is the three space dimensions and one time dimension, with higher dimensionality spaces that maybe this four-dimensional universe lives in, and essentially interactions with those higher dimensions onto the mere four dimensions that we're living in.
Well, if you have this expansion history of the universe derived from the map, is it conceivable that you would see that the universe, as it was expanding, did it in sort of a constant curve that was sort of sloping gently, as opposed to maybe something in a staccato fashion where it moved in fits and starts? For instance, if it did move in sort of a staccato fashion, would that tell you something? Does that fit any of the theories?
Maybe. I mean, the theory, you just have to come out with the measurement, and even if it's wrong, you get the theory papers the next day. I'm being too hard on someone. But right now, we are inferring the expansion history from kind of a couple endpoints. So from some measurements in the very early universe, and then some measurements in the more local universe. And then we're projecting this line between them, and that's where we really don't have a lot of data. Mm-hmm. So you can say the data all fits when, okay, here's a data point over here, here's another data point over here. I can draw a line through there and look, it fits those 2 points. But that's not really satisfying enough. So it's not even testing very well this idea of even this cosmological constant notion. And then it could be something much more interesting and dynamic than that. And that, I mean, it could be that something has happened more interesting as a function of time between these two endpoints, or it could be a field. So one of the terms that's batted around are quintessence fields, which are some sort of field that might actually vary in space as well, so that you might actually see something different when you look over here than when you look over here. And if you saw that, wow, that would be a big clue.
So if quintessence, for instance, was the explanation for dark energy, would quintessence leave a kind of a footprint on that three-dimensional map of the universe? Would it be a signal that you could detect?
So potentially yes, but it's I mean, right now I think the theorists are waiting for any sort of observations to really guide explanations right now.
But it sort of brings me back to this idea of Galileo. We have this instrument, and it's going to reveal a tremendous amount about the universe that we don't know today. It will really sort of literally lay out the picture for us. But the reality is that I'm sort of picking up here, we don't really know what we're going to find out. I mean, this is exploration in its purest form in some respects, and you know, I find that exciting.
Yeah, no, I don't think we know, and I think our hope is that we'll learn something that will tie back to other pieces of the puzzle that aren't explained yet. So, there is this whole other missing chunk of the universe, the dark matter. Is there any relation between dark energy and dark matter? I mean, people don't think so, but we haven't found either yet, really, except very indirectly. And then the other piece that I guess I'm sort of secretly hoping might fit together here is there is this unexplained phenomena from the very early universe, which the observable here is, as you look around in the universe, it looks like, basically, as far as we can tell, there are stars and galaxies and all these clumpy things around the universe, but really, the universe, it's pretty uniform. It's homogeneous wherever you look. And so you can even make these maps of the very early universe, the microwave background, where you see the universe was very smooth to about a part in a million, which is not really naturally described by anything. So there was what I'd call a cheat that was put in, which is this inflation theory. So this is just another piece of kind of our standard model of cosmology, was that, okay, there was the Big Bang, and then the universe that would have been very lumpy, but then we're going to say, actually, let's put in a period of inflation, so very rapid expansion of the universe in the first instance of the universe, where we could expand the universe so much that then the little piece that we're living in is uniform. And so, that works. And then you sweep that under the rug and like, okay, that's done. We've explained that piece. Okay, so that's why the universe is uniform. And then you move on. Oh, and then 8 billion years later, we have this other phenomena happening, which is also some inflationary thing in the universe. So those are two pieces that, I wouldn't be shocked if there's something related between those. The phenomena, in some ways, is similar.
Mm-hmm. We have time for questions as well from the audience, and we have runners here, I think, who have microphones. If anybody has a question for David, we could start that process now, or we can also continue our discussion. Does anybody have a question for David? There we go. There's always one at Berkeley Lab who kicks it off.
Could you tell us a little bit more about what you have at the other end of your fiber optics? Do you have 1,000 actual spectrometers there, or are you just measuring intensity? What's in that little black thing there at the end of the fiber optics?
Yes.
What's in there?
Okay, so what this does, so it is spectrometers. So the way to measure the redshift, the Doppler shift of a galaxy, is to split its light with something like a prism, so that you can get you can divide the light into all of its wavelengths, and then from that infer the velocities of galaxies. What we do here is you could have 1,000 spectrographs on the back end here. That'd be rather expensive because we're talking about instruments where we're trying to get efficiencies very close to 100%, meaning that every single photon that hits the device, we want to detect it. So the instruments, they're pretty expensive, state of the art. But what we can do is with these fibers, we take these fibers, they're plugged in everywhere on this focal plane, and then they all come out bunched together into a much smaller region. So on the back of all these fibers then is just a row of fibers that's just some number of inches long. And then that's what we feed into an instrument. And what that means is we have a spectrometer on the back of this, or 2 spectrometers, where the optics are only about this big. So it's a pretty modest size instrument. So you could build a spectrometer on the back of this entire focal plate, but that in of itself would probably be $50 million or something. I don't know what it would cost. Maybe it's not even buildable.
Another question? Right in the center here.
Thank you. I just wanted to ask, you mentioned that maybe of the first 7 billion years of the universe, universe was expanding, but it was
But slowing down.
slowing down.
Yep.
Right? So, so if you look out into the universe and you look far away, you're going to see slowing down. And then when you look closer, you're going to see the same effect, but expanding.
That's right. No, that's the observation that we have right now. So what we have, though, is we have the observations we have kind of an endpoint observation. We have an observation when the universe was actually 380,000 years old. So there's this map of the microwave background, which anyway, I could talk about, but we have that one measurement there, and then we have measurements in just the last 6 or 8 billion years of the universe accelerating. So that's where we have data right now. So that early part, we don't actually have the data really showing the universe slowing down.
Okay, and then you're building a 3D model of the universe. Is that just the visible part of the universe? I mean, my understanding is that we don't see the whole universe.
Oh, so all we get to look at with these telescopes is bright galaxies that have lots of stars. So that's what we're making maps of right now. That's a tiny, tiny fraction of the universe, and saying that is honestly tracing where a material is in the universe. That does bring in some additional assumptions that that you're actually tracing where the matter is in the universe.
We've got a question from the man in the blue shirt.
I was wondering if there are currently any experiments being done just on Earth that are looking to just see what we can find out about dark matter, as well as what kind of techniques you guys are trying to use to figure out more about the properties of dark matter.
Okay, so dark matter, so there are ground-based, what we call direct detection experiments. So I'm not an expert on this, so I don't want to say too much about it, but these are experiments of trying to see interaction events between dark matter particles and normal baryonic matter, where it's a challenging problem because by definition, what we know about dark matter is it doesn't really interact with normal matter. So any of those cross sections between the two are very, very tiny. So those are experiments that are looking for, it's kind of needle and haystack experiments of looking for these rare, very rare encounters between dark matter particles and normal matter particles, and you can design these experiments to try to optimize that detection. But I should say, from observations of the universe, that is where we have the indirect detection of where dark matter is. And what we can see is its gravitational influence of just the motions of galaxies. And so that's really where dark matter was discovered in the first place, was just how it's affecting the motions of galaxies. And even in just the last 5 years, we've actually learned a lot more about where the dark matter is, because what we can do is we can make maps from the gravitational influence of dark matter on material behind dark matter.
And we are talking about dark matter rather than dark energy here, but coincidentally, weren't some of the key experiments looking at galaxy behavior and dark matter done at the Mayall telescope that you're going to be outfitting for this dark energy experiment?
Yeah, so there's, so I guess it's a small world in astronomy, maybe. So the real censure for knowing that there was dark matter was looking at the rotation of galaxies, and so this was done with largely by Vera Rubin at the Mayall telescope in Arizona, where she made these observations of, so there are disk galaxies that look a lot like this, look a lot like our own Milky Way. And what she inferred was there must be a lot more material in these galaxies than just you would see from the stars and the dust, because they're rotating so rapidly that they just would have blown themselves apart if there wasn't something else to hold them together, something else with gravitational force.
Another question? I have just a kind of a personal question for you. I mean, you have an extremely interesting job and an extremely interesting topic. I mean, how is it that, and there are a number of people here who are just starting out their careers and maybe looking for what their interests are. What got you interested in this field, and who were your mentors?
Let's see. Well, so I'll start by saying I'm not someone who, when I was 6 years old, looked up at the sky and said, "Oh, I'm going to be an astronomer." That's it. So
you're doing this just for the money?
You got me.
I'm sorry.
Now I've lost my train of thought.
Okay. What was the inspiration ultimately?
Well, so I'll say a more recent inspiration for me has been working on this particular project, so the Sloan Digital Sky Survey, where this particular project, I mean, this has really fired up everyone working on it, because it's the first, it's both the first digital map of the sky, and then it's also the first big three-dimensional map of the sky that we've ever made. Mm-hmm. Human history has made. And so we're learning a lot from this. And it's, it's much more than just counting the butterflies. Apologies to anyone who counts butterflies.
The name of your program is BOSS. That stands for Baryon Oscillation Spectroscopic Survey. Maybe this will take this a little deeper than you or I might like, but I'm just curious about baryon acoustic oscillation, because, as I said, I'm an English major, and one of the things I know about science is that in space, nobody can hear you scream. So where does acoustic play in this notion of the expansion history of the universe?
Okay, so to measure the effects of dark energy, the only tools that we have are these geometric tools, where we have to look at things where we either know how bright they are or how large they are. And there aren't very many things in the cosmos that you can see out 10 billion light years and actually know that about. And so for galaxies in particular, you look at a picture of a galaxy, there's no good reference to know, okay, this galaxy is bigger than this galaxy or not. You can't actually tell. The thing, it's formed of a trillion stars. You can't see the individual stars.
So you need a point of reference.
Right, you need, and there aren't very many. So what we've latched onto with this particular project is a point of reference that we do know. And that point of reference, so the buzzword for us is baryon acoustic oscillations, but all that means is sound waves. Anyway, someone wanted to make it fancy, I guess. But what we're looking at are sound waves, and
so there once were sound waves in space?
There once were, and so this was when the universe was younger. It was a lot hotter. The electrons and the protons couldn't actually combine into atoms because the universe was too hot. So it meant that you had this plasma of charged particles. Within this plasma, you could actually propagate sound waves, just like us talking here. And
so in the very earliest days of the universe, either a ball or a disk, and I'm not sure quite what, of plasma, you could have an acoustic phenomena of sound waves propagating through that early universe.
And we did. And so you can compute from first principles what would have happened. And what would have happened is you propagate sound waves at something very close to the speed of light divided by √3 is about the speed of these sound waves in the early universe. And so we know that you had sound waves at that time, not from people speaking, of course. Well, maybe it's the aliens, I don't know. But then there was the age of the universe where then the universe cooled off enough that all these electrons could recombine with the protons. Then it's no longer this plasma. The universe becomes transparent. Sound waves stop propagating. They're frozen in wherever they are. And they're frozen in at a distance that we know exactly. And
So it's sort of like tire tracks in ice or something to that effect, that as the universe reached this moment when the protons and electrons found each other, light escaped. Is that your cosmic background?
Yep, that's
Cosmic
your
microwave background. The light escapes, and you have these sound waves sort of frozen in the material of the universe. And I gather that it's my understanding that they, to a certain extent, shaped the structure of today's universe, so that you can actually look at with proper instruments. You can look at and you can detect these oscillations in the structure of galaxies, and so that's essentially what you're looking for. But I understand that they talk about this as a cosmic ruler. So explain that a little bit.
Well, so it's a ruler because we can compute from first principles what that distance is. And so that distance, it's 500 million light years. There's some
A
more
rather
decimal
large
places.
ruler.
It's a large ruler, so a galaxy, an individual galaxy is much smaller than that. So over 500 million light years, that spans many galaxies. So what you're talking about are these ripples in the universe, where they're ripples in the distribution of galaxies. So it's kind of like the galaxies are your atoms in this case.
So if I had a big enough telescope and I could look at, could I actually see one of these things, or is it something that you need computer pattern recognition in order to find them?
It turns out if there were not dark matter particles in the universe, this phenomena actually would have been much more prominent. So it's kind of too bad.
It's complicated.
It's complicated, but the dark matter kind of wrecked it for us in this case, because if the universe were only baryons, then these sound waves would have been very wild fluctuations, so of order unity fluctuations even today. And then you'd look out in the universe and you'd really see these features strongly. Because of all the dark matter, that's actually damped out the effect of these sound waves relative to all of the matter in the universe, so that it's kind of only a few percent effect. So it's not easily visible.
So in this three-dimensional map of the universe that you're creating with these baryon oscillations, are they a little bit like the scale down at the bottom of a map that you see that will tell you how far things are apart? And if you're detecting these baryonic acoustic oscillation traces in the universe at different times in the expansion of the universe, you can use that ruler to essentially flesh out the map in a way that makes sense to you folks.
No, that's exactly how we're using it. Yeah, so it's a ruler.
Is that clear to everybody?
It's clear to you, I guess. So it's a ruler we can place at different ages of the universe, because as we look further out, we're looking when the universe was younger, and then we can place this ruler at each of those distances.
So it helps give you that sense of scale. It really is an essential part of a three-dimensional map, then, is to have that sense of scale that 500 million light
500
year
million light years
ruler gives you. And you know, it's certainly beyond my ken to understand this, but I'm starting to understand why the word boss shows up so much in the description of the project and the instrument, because this is a central part of your ability to make this three-dimensional map of the universe, which in turn will give us a lot of guidance in understanding the behavior of dark energy. I think you're describing to me as a void of information in really understanding what the hell dark energy is but this instrument and this project will take us a long way towards that goal. It's pretty amazing. We have time for maybe one more question.
If this recent expansion was caused by, say, the collision of two multiverses, would that collision also have injected more matter into our universe? And would that then possibly be dark matter? And would we have are there any theories of that we could detect that the amount of dark matter has changed over time along with the amount of dark energy?
Whoa. My short answer is I don't know. But so I haven't heard any theory that would, at least today, predict something about baryonic or dark matter changing over the course of the history of the universe. But at the same time, that's not something that anyone has looked at, as far as I know.
Well, is the hunt for dark energy so wide open that people are open to the idea of multiple universes? It is a term you hear batted around these days.
It is, and well, there are lots of reasons for this, and I mean, one of the reasons is throughout modern history anyway has been the notion that we don't live in a special place in the world, and so an extension of that would be that we don't live in a special place in our universe. We shouldn't live in a special universe even if there are lots of universes. If we do live in some sort of multiverse where there are different universes that have, the first question is, well, is there even any way that those know about each other at all? And they wouldn't today, sort of by definition, or it would be part of the universe. On the other hand, if this multiverse view of the world is correct, then you could certainly imagine that it would have some sort of imprint on the formation of the universe in the first place. So yeah, that's as far as I'm willing to go on this anyway.
Last question? Before we, do we have one?
No, I'm just going to do it.
Oh, okay. Before we go, this is an experimental format. Next week at the same time and same place, Venkat Srinivasan, one of the world's leading experts on batteries, will be here to talk about the future of batteries. And I hope that some of you will come to that and that some of you will tell your friends about this presentation. And basically, I just want to thank you for coming here, and I want to thank David Schlegel for coming and enlightening us on the hunt for dark energy.